In this video, we're going to take a look at a concept called variation, and it has to do with proportions. So scientific laws are often stated in terms of ratios and proportions. So for example, direct variation, we say y is proportional to x, or y varies directly as x, if y is equal to some value k times x. This value k is called the constant of proportionality. So an example of that is, let's say you have an hourly wage, and the total number, your total amount earned, is equal to whatever you earn hourly times the number of hours worked. Okay, so you could model T equals total pay is equal to K times X. So let's say that you work in an hourly job where you make $12 an hour. Then your total pay every week, or however every 2 weeks, would be 12 times the number of hours worked. So that we would say that your total amount that you get paid is proportional to the amount of money that you earn. Okay, so here's some applications that you would be familiar with. The first one, the circumference C of a circle is proportional to or varies directly as the radius r. We write this as C is equal to K times r. But you know the definition from a previous class. The circumference of a circle is 2 pi times r, so we call 2 pi that constant of proportionality. Okay? Inverse variation, we say that y is inversely proportional to x, or y varies inversely as x, if y is equal to k divided by x. K is still called the constant of proportionality. Inversely proportional means we're dividing instead of multiplying. So here's one of the science examples of Boyle's law. Boyle's law states that at a given temperature, the pressure P of an ideal gas varies inversely as the volume. So we write this as P is equal to K divided by V. In this case, the volume of the gas, as the volume of the gas increases, the pressure decreases, or as volume decreases, the pressure increases. So if we were to look and see what that looks like, notice direct variation is linear with a constant slope. As your hours increase, your pay increases. Inverse, we won't look at graphs of these, has a graph that looks basically like this. It's not linear, but it's a curve. Okay, so in this case, as pressure increases, volume decreases. No, as volume, yeah. Sorry, let me get as volume increases, pressure decreases. Okay, so that's inverse variation. Joint variation is if you have more than one thing acting at the same time. So y varies jointly as x and z if y equals k times x times z. So this time you have two things. K is still the constant of proportionality. So this can be example in the law of gravitation. So Newton's universal law of gravitation can be stated as follows. The force, capital F, of gravitation between two objects, so there's our force, varies jointly as the masses m1 and m2 of the objects, so that means m1 times m2, and inversely as the square of the distance r between their centers, divided by the square of r. So G right here is the constant of proportionality. So let's see how this works with a couple of examples. So we're going to write a general statement for each of the following using direct, inverse, or joint variation. So the first says the electric resistance R of a wire varies inversely. So that means that my general equation is K over X. I just want to make sure I get the correct variables in there. Varies inversely as the square of its diameter D. So capital R is equal to k divided by the square of the diameter d, d squared. Next example, the volume capital V of silt carried by a river is proportional to, so direct variation and proportional to mean multiply. So the general equation is k times x. So the volume V carried by a river is proportional to, so k times, the 6th power of the velocity of the river. So small case v to the power of 6. So notice k, we don't know. We just know there's a constant of proportionality in there, whether it varies inversely or varies directly. Last example, the average electric power P entering a load varies jointly as the resistance R of the load and the square of the effective voltage V, and inversely as the square of the impedance Z. Okay, so P equals K, our constant of variation, varies jointly as the resistance capital R and the square of the effective voltage V, and inversely as the square of Z. So there's our joint variation equation. All right, so what do we do with these types now that we understand what the variation types of statements are? So usually we'll have a problem where we have to find the constant of variation. So this is how we find a value given other values. So we're not going to wrap it around a word problem. We're going to get real general terms. If y varies inversely as x, and x equals 15 when y is 4, find the value of y when x equals 12. So this is about a 4-step process. The first thing we do is write the general equation. This is varying inversely, so that's k divided by x. Then step 2, put all your known values in. We have a value for y and a value for x is 15. So what we want to do now is we want to find out what k is. So we can multiply both sides by 15 to solve this equation for k. K is equal to 4 times 15, which is 60. So now we know that y is equal to 60 divided by x. So now we know the constant of variation is 60. So that's step 3. The last step is evaluate, find the value of y when x equals 12. So we use the equation that we found with k, and we substitute 12, which equals 5. So the y is 5 when x is 12. So that's a step-by-step process of using variation to solve a problem. Next example. The distance d that can be seen from horizon to horizon from an airplane varies directly as the square root of the altitude h of the airplane. All right, so then we're given some values. If d equals 133 miles for h 12,000 feet, then find d when h is 16,000 feet. So step 1, we write our variation equation. D equals k, constant of proportionality, times, because it varies directly, the square root of the altitude h. So that's our general equation. We don't know what k is yet. Step 2, substitute the values given. 133 is equal to k times the square root of h, which is 12,000. This is going to use this equation to find k. Divide both sides by 12,000. The square root of 12,000. So k is equal to 133 over the square root of 12,000. I'm not going to multiply that out. I'm going to wait until I get to the end of the problem. Okay, so 3, now I know that d equals 133 over 12,000 times the square root of h. I just substituted the value for k. Last but not least, now we can answer the question. Find d if h is 16,000 feet. So we substitute square root of 16,000 in for h. Now I'm going to put all of that in the calculator at once. No rounding. So I get 133 times the square root of 16,000. Then I'm going to divide that by the square root of 12,000. And I end up with, I'll round to two places, about 153.58. And this would be in miles. Okay, that one's a little bit more complicated because we have the square roots in there, but the process is the same. All right, last example. The force F on the blade of a wind generator varies jointly as the blade area A and the square of the wind velocity V. So first thing we do, we're just going to write a general equation for that. So capital F equals K times constant of proportionality, varies jointly as the blade area A, capital A, and the square of the wind velocity, small case v squared. So there's my general equation. Step 2, we're going to be given some information. It says F is equal to 19.2 pounds when A is 3.72 and V is 31.4. So to find K, we're going to take 19.2, divide both sides by our product. K is going to equal 19.2 divided by 3.72 times 31.4. And you'll notice I set these up and put it in the calculator last. That's so I don't have any rounding errors. So I want 19.2 divided by, and then I'm going to put parentheses, 3.72 times 31.4. So I get approximately 0.164 if I go 3 spaces. Okay, so it said find the equation relating F, A, and V. So now my equation is going to be F equals about 0.164 A V squared. I had to find the constant of proportionality to be able to have the final equation.